These are the solutions for question number 2 from the 2014 examination paper. So we want to determine the location and type of critical points of this Hamiltonian system, and then we want to determine the stability of this system using a Lyapunov function. So for part A, we have x dot is y, which for the Hamiltonian system is dh partial dh dy, and y dot is equal to this expression, which is minus partial dh dx. So to find h, we simply integrate. So partial dh dy is y, so that means that if we integrate, we get the first term y squared over 2. And then if we integrate dh by dx to get h, then we get x minus 1 squared over 2, and we get an x minus 1 to the 4 over 4. So this is the Hamiltonian of this system. To determine the critical points, we solve x dot equals y dot equals 0, which you can solve using the solve command in MATLAB, or you can do it by hand, and we get 3 critical points. And here are the 3 critical points. To determine the type of critical points, we use the Jacobian matrix. So J is dp dx, dp dy, dq dx, dq dy, which I've done for you here. When at the origin, so at 0, 0, we substitute x and y as 0, we get this matrix. If you work out the eigenvalues, they're purely imaginary, so this is a centre. Remember, for a Hamiltonian system, critical points are either centres or saddle points. So this one is not a saddle point, so therefore it is a centre. For x is 1, y is 0, here is the Jacobian matrix, and we get the eigenvalues are minus 1 and 1, with eigenvectors minus 1, 1 and 1, 1. So these give you these manifolds here, and you can see that when lambda 2 is 1, we get the eigenvector 1, 1. So this is the unstable manifold, because the eigenvalue was plus 1, which is positive. So we know that this is the unstable manifold, so we move away from the critical point. For the other eigenvalue, minus 1, here is the eigenvector, which is minus 1, 1, and this is the stable manifold, so we go towards the origin. And from this simple fact, we can complete the direction on all of the trajectories. For the critical point at 2, 0, then here is the Jacobian matrix, which again, if you work out the eigenvalues, then this is again a centre, because it's not a saddle point. So here are our 2 centres, and here is the saddle point. And for a Hamiltonian, remember, there are no stable or unstable points, so this unstable branch has to come back and go in here, because there are no stable or unstable points for a Hamiltonian system. For part B, we have this system of differential equations, and we're given a Lyapunov function kx squared plus y squared, and this gives you ellipses around the origin. So to work out dv by dt, we use this formula, partial dv dx dx dt plus partial dv dy dy dt, which you can obtain from the chain rule from the second year. So we substitute for partial dv dx and dx dt and partial dv dy and dy dt. Simple algebra gives us that dv by dt is minus twice epsilon y to the 4 times 1 plus x squared. And remember, k and epsilon are positive. So therefore, v dot, you'll notice that v dot is less than or equal to 0, but it can be equal to 0 when y is 0. However, on y equals 0, so if we put y equals 0 into the y dot, then we get y dot is minus kx, which means that if you start on the x-axis, you have to move off. So as soon as you move off the x-axis, then you go in on the Lyapunov curves. Okay, so as soon as you move off, then you've got to cross the Lyapunov curves inwards. So therefore, this origin is asymptotically stable. And that concludes the solutions for question number 2.